going to continue on decimals and fractions. So basically we have learned the definition of decimals, we have learned arithmetics, basically addition, subtraction, multiplication, division between decimals. So in this class, we'll continue learning decimals and fractions. So to be more specific, we will learn how to convert between decimals and fractions. Right, so for example, we have learned in the last class that decimal number can be converted to some integers and help us do the multiplication divisions. And the way that how we convert them into integers is try to move the decimal point to the back of the last digit. And by doing so, by moving the decimal points, meaning that you're multiplying a power of 10, right? So for example, if I want to move 2 steps to the right hand side of the last digits, this is equivalent to having this number multiplying by 100, which is 10 square, right? Which is 10 square. And of course, you cannot just multiplying a number by 100. In order to have this outcome still equal to the original number, you need to divide the same number at the same time, right? So equivalent to you multiply a 1 to any number, it's still the number itself. Then you can separate this by keep the number on the denominator, but then combining your decimal with the power of 10. And in this case, intentionally to make a 100 or 10 square here because I'm moving the decimal point 2 steps to the right. So this 0.04 multiplying by 10 square 100 will then equal to the integer number 4. Right, so this number, this decimal number 0.04 can be written in this form 4 over 100. And of course you can further simplify this. If there's common factors, you can further divide this by 2 or divide by 4. Actually 4 is a common factor, so eventually this fraction can be further simplified as 1 over 25. And up to here, we are actually successfully converting a decimal into a fraction. So this works the same way to negative numbers. Assume that have a negative fraction, negative 1.72. In this case, I'm gonna write it a bit faster. So minus and minus, I can keep the minus sign outside first or in the front first. And then I have 2 decimal digits. So this means in order to convert this 1.72 into 172, I need 100, right? I need moving 2 digits, which means I need a 10 square, and that equivalent to 100. So basically, how many steps you want to move equivalent to how many zeros you're going to have. Right? And then, of course, this can be further simplified by canceling out a common factor. I think number 4 is a common factor, so that's 43 over 25. So it's minus 43 over 25. Right? Because so far the 2 examples are all converting the decimal with 2 decimal digits. This time, if we have more digits, it's still the same thing. If I have 2.5625, if I want to write this whole thing into an integer, that means I'm moving this dot 4 places, right, or 4 steps to the right. This is equivalent to multiplying 10 to the 4th power, or 4 zeros. That is 10,000. And then the same thing, you can further simplify this. I'm not going to show too many steps. To simplify, you can see obviously number 5 is a factor, and if you keep dividing 5, you'll see 25 is also a factor. So eventually you'll be able to simplify this into 41 over 16. Right? So then you probably so far would see that the conversion is quite straightforward. You can, given any decimal, you can write it into an integer on the top of the fraction, or as the numerator, and then the denominator is determined. The denominator is always a power of 10, and the power is determined by how many digits you have, or how many decimal digits you have. Right, so this is how to convert from decimal to fraction. Then similarly, from fraction to decimal, you can try. One way is to convert the denominator into power of tens. So for example, if I have a fraction 1 over 2, of course you can also use the division, because this example is too simple. But let's see a universal way to converting that is to try to get a 10 from here. 2 times 5 will give you a 10. So correspondingly, you have to also multiply 5 to the numerator, making it still equal to the original number. Then you will have 5 over 10. And as long as you have a dividing by 10 is multiplying by 10 to the power of -1, and this is the first decimal digit if we go with the definition of the decimal number. So then this can be converted into a decimal number. Or if we have a fraction whose denominator is not so obvious to be converted into a 10, like for example, when I have a 2, I know that simply 2 times 5 can give me a 10. So if I have an 8 as the denominator, how can I convert this to a power of tens? Right, so basically I need to know 8 times something should equal to 10 or 100 or 1000 or any of these combination. So obviously this must be an integer, and there's no way that 8 times the integer equal to 10, because 10 divided by 8 will not give you a integer outcome. So 8 is not divisible. 8 is also not divisible to 100, but 8 is actually divisible by 1000. I can verify this by trying the long division. Right, it's 125. So this means if I'm multiplying 125, I can convert my denominator into a number that is power of tens. So 7 times 125, you can use your calculator, or you can do it on your scratch paper. So it would be 875 over this. We just proved that it's 1000. Now we have something divided by 1000. That means that's the 10 to the power of 3. And you're dividing this means you're moving your decimal point to the left hand side by 3 steps. 1, 2, and 3. So it's 0.875. Okay, there will be more complicated cases, because right now the examples I'm showing are always convertible to a power of 10. Later on you will see more examples. You will see that this obviously not always true. But let's see some couple more easier example first. This one asks to express the reciprocal of 3.2 as a fraction. So first of all, you need to find the reciprocal of 3.2 and then express that as a fraction. So there's two ways. Either you find the reciprocal, then try to convert into a fraction. But I would prefer the other way is to convert this number into fraction first. And then to find the reciprocal is really just turn this turn that fraction upside down. That seems easier. So first of all, I'm trying to convert this into a fraction first. So this, by what we just learned, there's one digit after the decimal, so it can be written as 32 divided by 10. And then if you want to simplify, 2 is a common factor, so it's 16 over 5. So this is still the number of 3.2. So then the reciprocal of 3.2 would be 1 over 3.2, that is 1 over replacing 3.2 by its fraction form, and then this is really just 5 over 16, right? So it's just, I'm just writing this out explicitly, but simply speaking, the reciprocal of this number is just flipping over, so it becomes 5 over 16. Okay. Let's see one more example. How many 8s are there in the number of 5.75? So first of all, what is 8s? So 8 is 1 over 8. So how many 1 over 8 in this number? So this would be asking you, for example, let's show a simpler example. How many 2's are there in number of 4? There are 2 2's because 4 divided by 2 is 2, right? So essentially, the question is just asking what's the result of 5.75 divided by 1 over 8. So this divided by 1 over 8 would be equivalent to multiplying by 8. And then you can either just do the calculation right away, it's also doable, or from what we learned is that we can convert decimal into integer first, and then to do the multiplication. In this case, 575 times 8 is 46 hundredths. It just happened to be multiple of hundreds, then 4600 divided by 100 is just 46. Okay, so here are the examples of converting between fractions and decimals. Now we're going to see a new concept which is called repeating decimals. And remember that where we see the examples here, when we try to convert fractions to decimals, in this special case where you can convert the denominator into power of tens, you're able to write a fraction into a decimal that has a limited number of digits. But there's also cases where you cannot write a fraction into limited number of digits of the decimal. Some decimal could have infinite many digits. That we call the repeating decimals. So for example, to round 1 over 3 to the nearest tenth. Okay. We'll show this step by step. So first, let's try to round 1 over 3 to the nearest tenth. Like remember the roundings we have learned in the previous class. So first of all, 1 over 3, I'm still trying to have a power of 10 on the denominator. Let's see what's happened. If I want to convert this part to be 10, which means I need to multiply a 10 over 3 to it to convert this to 10. So which means I will have another 10 over 3 on the top. And then this canceled out, so this would be 10 over 3 over 10. And then 10 over 3, remember, we can also write this into 3 with 1 over 3, right? Because 10 is 9 plus 1. And we can write, we can only leave the fraction that is less than 1. So we know that this is a number somewhere between 3 and 4. Right? So because we know, in this way, we'll know that 3, basically 10 over 3, is a number between 3 and 4. So that the original number 1 over 3 this is 1 over 3 is between 3 over 10 to 4 over 10. I'm just by looking at this number, I know it's between 3 and 4, but this number should further divide by 10. So replacing all the numbers, simplifying all the numbers and replacing this with the original amount 1 over 3, you would be able to tell that 1 over 3 is actually a number between 0.3 and 0.4. Okay, so this is to round 1 over 3 to the nearest tenth. Basically, the nearest tenth means, the tenth means 1 digit after the decimal. Now, how about keep rounding this to nearest hundredths? We actually do the similar thing right here, because we want to round to tenth. That's why we leave a number 10 on the denominator. Right, so later on we'll only have 1 digit after the decimal point. So if we want to round to nearest hundredth, seems like we want to have a 100 on the bottom. So it's the same way that I need to create a number 100 over 3 to the bottom, so later on I can making sure that denominator is 100. Similarly, I need to multiply the same number on the top. So eventually 100 divided by 3 is 33 and 1/3 over 100, right? And very similar to what we had in the previous example, that 33 and 1/3 is a number between 33 and 34, right? So then this is just the number on the top. So altogether divided by another 100, I will tell that 1 over 3, right? This divided by 100 is our original amount, 1 over 3. And then 33 divided by 100 is 0.33. 34 divided by 100 is 0.34. So I can tell that if rounded to the hundredth decimal, then my number 1 over 3 is actually between 0.33 and 0.34. Now do you see a pattern? If I'm keep going, if I want to round to thousands, basically 3 digits, or round to 10,000, 4 digits. It will keep going as 0.333 to 0.334 or 0.3333 to 0.3334. Right? You can see that this number will keep growing, keep going with the same pattern, but 1 over 3 is always between two given numbers, and there's no end. Right? This pattern can happen forever. So this means that 1 over 3 is a fraction such that it has repeating decimals and infinite number of decimals. Right, I can write 1 over 3 as many as multiplication of tens in this way, right? So then 1 over 3 is essentially 0.333, and repeating 3 with infinite many digits of 3. Okay, so here, this is the concept of repeating decimals, and this is also the concept of infinite decimal. We can also show this or prove this in algebra way. So algebraically, if we let x equal to this infinite, well, I can first let x equal to 1 over 3, where 1 over 3 can be written as infinite many digit of repeating 3's. Then 10 times x is 10 times this number. And we just learned that 10 times the decimal number means that you can move the decimal point 1 step away. So that's 3.333 with infinite many 3 again. So if you're subtracting the two numbers, 10x subtracting x, 10x equals to 3.333, infinite many 3, and x will set this to be 0.333 with infinite many 3. Right? Then the subtraction, because we all have infinite many 3's, they can be cancelled out. But here the first digit, 3 minus 0 is 3, so it's 3.0 with infinite many 0. But 0 after the decimal point means nothing, so it's just 3. And what we have on the left-hand side of the equation, 10x minus x is 9x. Right? So that means we have 9x equals 3. So we can solve from here that x is 1 over 3. And this proves that 1 over 3 equals 0.333, infinite many 3's. Okay, so then we have learned a new concept. So combining with the decimal that with finite number of digits, we have the two different concepts. So the repeating decimals means the digits repeat forever. It's infinite many, so it's repeat forever. The other scenario, we'll call it terminating decimal or finite decimal. These are the decimal that has finite number of digits. And there's a way to write the repeating decimal, because in most of the cases we don't want to write such many digits or such many numbers with dots, it's taking too much space. So there's actually a way, symbolic way, to write the repeating decimal. That is, for example, 1 over 3 is 0.33 with infinite many 3, and we can write a bar on top of 3. This indicating that this artificial symbol that indicating that this digit 3 will be repeating forever. For example, if you see later on, this bar can be on any number that is repeating and don't have to be covered on all the numbers. Like for example, if some case you see a number 0.279 with 7 and 9 having a bar on the top, this means the repeating component is really just the digit 7 and 9. So there's nothing odd with the first digit 0.2, and then 7, 9 is repeating. So 7, 9, 7, 9, 7, 9 repeating, right? So first of all, this bar don't have to cover all the digits. It can only cover the partial digits, but it has to be the last digits. And it also don't have to be only one digit repeating. It's possible to have 2 digits repeating or 3 digits repeating, or as many digits as possible that is repeating. So do we know, other than that 1 over 3, do we know other cases or fractions that can be written as a repeating decimal? For example, 19 over 11. In this case, we'll have to use the long division first because fractions are essentially divisions, right? So we can use the long, but before using the long division, we can simplify this fraction, right? Because 19 is greater than 11, so it's 1 and 8 over 11, right? So we already know that on the ones place, or on the left-hand side of decimal point, it is 1. We only need to take care of the component that on the right-hand side of the decimal, or the component that is less than 1. So 8 divided by 11. Right? So first attempt would be 7, 77, give you 30, then be 2, 22 give you 8, 0. Okay, 7 give you 77, that's 3. Then 2 give you 22 and give you 8, right? I can keep going, but you see that the pattern is already clear. It's repeating 1, and 8 over 11 is 72, 72, keep repeating. So then you can write this as 1.72 with the bar on the top of 72. And we can also do it backward. For example, given a infinite repeating decimal, can we convert this back? And yes. So for example, if I have a repeating decimal 0.2, so that is keep repeating. So how to convert this to a fraction? I remember I just showed the example of proving that 1 over 3 equal to 0.333. So I can use the same way. So I can let the variable x equal to 0.222. Keep going. And then that means 10x is 2.222 with infinite many 2's. So then 10x minus x is equivalent to have 2.222 minus 0.222. Keep going, right? And then 2 minus 0 is 2. The rest are all zeros because they both have infinite many of 2's. And to the left, 10x minus x is 9x. So I have 9x equals 2, so that x is 2 over 9. So essentially, this repeating decimal 0.2 with 2 repeating can be written as a fraction of 2 over 9. Like we can see a more complicated case to further show this methodology. Basically, this methodology can help you to determine all the repeating decimals and converting all the repeating decimals into fractions. For example, if I have a more complicated case, I have 5.0025 with the digit 2 and 5 repeating. So this number can be written as 5.00252525 and repeating, right? So similarly, I let x equal to this, then this time I can't just have 10x because I want to cancel out, I want to take advantage of the repeating terms and making them cancel out each other to be 0. So I need to reach the repeating term to start the subtraction. So this number, if you're only multiplying by 10, it's not reaching the repeating term. In fact, you should at least go to the second decimal. So 100x would be 500.252525. And then x is 5.002525. So 100x minus x is 2525, 5.002525, right? Now you see why I'm doing this, or why I'm multiplying by 100, because up to here, all the digits are repeating similarly with the number 25, so there will be infinite many zeros, no problem. But before this dashed line, up to here, you still need to do the calculation, do the subtraction to determine the values, right? So 25 minus 0, 0 is 25. This minus 5 is 495. On the left hand side, 100x minus x is 99x. So I have 99x equals 495.25, right? And that means my x is 495.25 over 99. I want to have a fraction with all integers, then I need to multiply 100 on both sides. So this number would first be converted into integer, and then I can further simplify this. If this can be simplified, I can divide by a 5, and then you can just simplify this fraction. So eventually this is how you find how you convert any repeating decimal into a fraction. And this shows that all the repeating decimals can be converted into fraction. Right? Even though they have infinite many terms or infinite many digits, they are still able to be converted into fraction. So a side note that, don't know if you notice that we have one more scenario that's not covered in here, and it actually won't be covered in this class. It will be mentioned in a very late stage. So first of all, your fraction can be either written as a finite decimal, right, with finite number of digits, or if you have infinite many digits, you still have one scenario that is infinite but repeating, like all the examples we just saw. So if you are infinite and repeating, you are still able to convert this into fraction, right? So they all convertible. I put 2 arrows here, means convertible. But there is one case that is not convertible, that is infinite many and non-repeating. So there exists a special case of the decimal number. There have infinite many digits, but none of those digits or none of any combinations of that decimal has a repeating terms. So it's non-repeating infinite decimal. So this case, infinite non-repeating decimal are called irrational number. Okay, irrational numbers. Like, for example, pi, you will learn that later. Pi is an irrational number. It has infinite many decimal digits, but it is non-repeating. So any, which means oppositely, the rest of the numbers are rational numbers. Right? Basically, the other scenarios, they are rational numbers, and all the rational numbers can be convertible to fractions. So fractions, you can see fractions becomes a alternative criteria to tell whether a number is rational or irrational. So you're not asked to handle this in this class, but it's good to know, and you will learn this in the future. So basically, whether a number can be written as a fraction or not will indicating that this number is a rational number or irrational number. In the last example, let's convert single-digit fractions into decimals to see how they're gonna looks like. We'll start from 1 over 2, because 1 over 1 is just 1, right? 1 over 2, it's 0.5, right? 1 over 3, we just showed that it's 0.3 with repeating digit. 1 over 4, you can do this by yourself or using calculator, but 1 divided by 4 is 0.25. 1 over 5, similarly, this is 0.2. You can do the division by yourself. And 1 over 6, we haven't tried this before, but you can do this in terms of a long division. Right, you see the numbers start repeating now. So it's 0.16 is 6. So 0.16 and the 6 is a repeating term. 1 over 7, similarly, we haven't tried this before. One, I got 30. 4 times 7 is 28. 2 times 7 is 14. So far, we don't have the repeating remainders. As soon as you see the remainder is repeating, that means your output will start repeating, right? So far, remainders are 3 or 2 or 6. None of them are repeating yet, so let's keep doing. 8, 56, 40. I can have 5, 35, 57, 49. Now I see the 1, number 1, right? So if I keep having a 1, I start repeating with 3. And I can keep having 4, and we'll get the same results. So this is a very long repeating number, but it is still repeating because every fraction can be converted into either a finite decimal or infinite decimal with repeating. So it's actually having 6 digits repeating. It's a complicated one, but we just show that. Then keep going 1/8. You can do the long division by yourself. It will give you 0.125. 1/9. You can use the same way, or if we know 1/3 is 0.3, with the 3 repeating, 1/8, 1/9 is actually 1/3 divided by 3. So it's 0.33 divided by 3. Because 3 is repeating, so this equivalent to 0.1 So it is 0.1 with 1 repeating. Right, the last one, 1/10, is just 0.1. So here I'm just showing the basic results for the single digit fractions and how the results look like. And you can see that some of the results are using a cross, right? Some are finite, some are infinite repeating. If I take out the infinite repeating outcomes, you can see a pattern that unless if your denominator contains a power of 2 or a power of 5 or the power of multiplication of 2 and 5, right? 2, 4 is 2 squared, right? 5 is 5, 8 is 2 cubed, 10 is 2 times 5. You have to have either your prime factor contains only 2's or only 5's or only the combination of 2 and 5. And that's the only case that your fraction can give you a finite decimal. So that means in most of the fractions, they are not finite decimal. And they will be having infinite many digits but repeating. And only this case will give you a finite decimal. So that's all for this lesson.